So we have about half an hour here for a panel discussion, a short panel discussion. I am going to start out with a question that the speakers can take and run with in pretty much any direction they want to. Whoever sits next to me will get to respond first. And then we will ask for additional questions from the audience. And at 5 o'clock, remember that there's drinks available, wine, I believe, available, some finger foods, and a poster session out on the Dean's Lawn where we had lunch. So a lot of students and postdocs have a lot of cool posters out there. And so we can socialize, continue the conversation, and take in some more science then. So first of all, thank you all so much. I mean, I'm just thrilled to have had this event today and to have had all of you here. Each one of you were picked for a particular reason, and you've delivered so much really great intellectual meat here for us to chew on. I want to ask kind of a personal question in a sense, and you can take this in a number of ways, but what I would like for each of you to answer is, what is a problem that you have in your research right now that if that problem were really crushed or really solved, it would open up vistas for you, places that you'd love to get to, and you just can't get there right now. And this could be a problem that's not in your field. It might be something you wish that the neuroscientists would answer for you. It might be something that you wish the data people would answer, or the machine learning people. I think we should rule out faster computers. or more memory, or better data storage, something like that. But I would like to hear that from you. You could also take that in a direction of, if there's one problem I'd really love to know the answer to before I exit this business or exit this planet. Here's what I'd really like to know the answer to. So these are quite personal, and it might be highly relevant to your current research agenda, just points of frustration or points of hope, or it might be a question you want to ask someone else on the panel. But I'd just like to hear your answers to that. You want me to start with Jim? Maybe I'll start with Greg. Greg's never at a loss for words. Deer in the headlight.
Okay.
Go for it.
How about, okay, I've got it. Artificial emotional intelligence is an area that I feel like, from the point of view of, so I very much agree with 2 out of 3 of Fei-Fei's pillars, and that's about making it impactful for humans. And judging it that way, and also really trying to enhance and augment what our experience is as a society. And I think that a big part of what's missing in AI technology today is actual understanding of the emotional context and of human-human interaction and communication. And there's some early, sort of, I think, very primitive work on artificial emotional intelligence, but it's really very much in its infancy. And I believe that if that part of the field grows and expands, and we're able to understand how people can relate to each other in constructive ways, we're both going to make technologies that are more practically useful. And I actually think that we're going to be able to help people that have a really wide array of psychiatric and behavioral issues that really need support, and we might be able to build machines that are able to support them effectively. And I would love for the field to move in that kind of direction.
So we could talk about that for a good half hour, and maybe we'll come back to it. But let's go to another panelist first. That's a great one to stick up there in full view. James?
Yeah, so the question is, what one thing would I like to solve, or what is needed to maybe solve it? I think there were 2 questions there. So I guess I'm sort of one of the only pure maybe neuroscientists on the panel. I'm still motivated by how the brain actually works. And there's an old idea, which is pieces of cortex look very similar to other pieces of cortex. And if there's going to be some principles of understanding, they're going to maybe live at that scale, sort of analogous to something like how we think about DNA code for molecular biology. And we haven't solved that problem yet. And I still would like to figure out how you can take a bunch of little pieces of tissue and arrange them horizontally, and that's V1, and then stack them vertically, and that gives rise to a whole ventral stream. And that system somehow learns largely in an unsupervised manner, but also from its birth state, it's in a good place with some inductive bias, and as Matt put it. And that problem is still the Holy Grail problem for me. And to get to that problem, I'd like to know what's the neural activity at the birth state of a monkey. And that's a very hard set of data for us to get at the scales we want. And then the learning trajectories through the development of the animal. And so we have little hints of data, but it's very hard to approach this problem, at least in that species. But the core deep question there is, how does a little piece of cortex, maybe it's a magic learning engine that scales naturally across evolution and could scale even beyond what it currently does in the visual system. So that's my version of the Holy Grail that got me into this, and it's still unsolved problem.
So why start at the birth of the monkey? The nervous system has been active for months before then.
Well, exactly. So then you get to, just the birth would give you, what happens after birth, and then you want to go before that, and then you get to a point, well, do I care? I'm going to start studying evolution after that, right? So, but even knowing, we assume that a lot of people are talking about learning here, and I was not talking about learning, but that question about learning and development is hard to approach in the monkey in vision, as you know, Bill. So I think that is a Holy Grail for. This would be a big achievement of neuroscientists. We could say what a piece of cortex really does in a learning sense,
absolutely.
right? And that is unsolved.
I'm biting my tongue to resist asking you another question, a follow-up question on that. Duina, would you like to? Yeah.
So I have two problems. I hope that's okay.
Yep.
One is exploration. So for reinforcement learning agents, they need to gather their own data. And whatever data comes in is really important for whatever they learn. And in biological systems, there is purposeful exploration. If you look at babies interacting with the world, they'll study an object, like little scientists, like was mentioned. Whereas our algorithms are randomized, and that's it. And so having some way of formulating in a computer that we want to have purposeful, directed exploration, I think that would both increase efficiency as well as really make our results a lot better.
That one's great all along, and it ties into the word that Fei-Fei said near the end of her talk, curiosity.
Yeah. The second issue is sort of a formal mathematical definition of what is the objective of continual learning or of transfer learning, or both. And these days, like, math gives us lots of good tools. If we have an objective, we can optimize for it somehow. We'll find a way. But in this case, we just don't know what that is. And I feel like that's really holding us back.
Great. Thank you. I think Fei-Fei has volunteered to go next.
So I'm going to go orthogonal because I already talked about a lot of these technical want-to-dos. So
You did, yeah.
one of the things that really is very much on my mind, especially returning to Stanford, is actually people. Is about the thing about AI, and also I think a little bit of neuroscience in the past few decades, is that we are starting to get very siloed, and our graduate students and undergrads coming out of our programs just know computer vision and object detection, or natural language processing. But if we look at where AI's future is and its future impact, what we really need to train is these thought leaders that can cut across disciplines, that can cut across technology, science, humanity, social science, to think in a framework that is, I would say, human-centered. And I feel that as a university, and we want to learn from SNI or the Wu Tsai Institute,
Very good. Very good.
is how do we train next generation scientists, engineers, policymakers, thought leaders that have the bigger purview of what technology is about, what science is about, what the impact of these our scientific or engineering work is about. So
Great.
Yeah, I think these are all actually great. I'd love to see all of them solved. One thing I'm actually kind of very perplexed by is the credit assignment problem. I mean, stated dramatically, we have 10 to the 14th synapses in our brain. Let's say you hit a tennis ball wrong. Which one of those synapses screwed up? How do you fix it? How do you fix them, the population? How do you translate errors that you get in visual coordinates at some later point in time, long after you made the error, back to the motor system that created the error? How do you do this more generally? Moreover, biological systems, I think, solve this problem in a very different way than our artificial networks do using backpropagation. Synapses only have information that's locally available to them, to the pre- and postsynaptic neuron and the electrical activity in both the pre- and postsynaptic neuron and the neuromodulators that come in. I mean, if we could really crack this problem, we could build next-generation neuromorphic devices that implement credit assignment using local rules at low power, high efficiency, and we'd actually know how to program them. This would have dramatic implications for technology. Conceptually, I think it would be revolutionary, and we don't have very good ideas for this problem or how the brain solves it. I'd be super excited about that.
I hope some PhD students are taking notes out here. Yeah.
So when I moved to DeepMind, I thought that the questions that I had been interested in my cognitive neuroscience work on prefrontal cortex and cognitive control, that they would somehow sit separate from the issues that were going to be most central in the AI work that I was engaging in. And what I found is the opposite. The things that were most mysterious and that kind of qualified as these Holy Grail questions for me and a lot of my colleagues in that area of cognitive neuroscience are coming up as Holy Grail questions in AI. And the one. So I've been to a lot of meetings on prefrontal cortex and cognitive control, and you spend the whole time talking about the Stroop effect and things like that. And then you go out for beers, and somebody says, yeah, but the thing that we really don't understand, that we should be able to explain, but we really have no insight on, is what our experimental subjects do during the first 15 seconds of the experiment. When you give them the instructions, and then they start working on the computer, and they just figure out what's going on. And I think we have the same challenge in AI now. Just to give an example, there's a group at DeepMind that's been using deep learning to solve Raven's progressive matrix problems, which is an intelligence test. Many of you will be familiar with it. It's kind of a logic test where you're given a bunch of shapes, and then you're supposed to decide which of a set of candidate shapes kind of completes the sequence, and you have to figure out what relational rule is relevant. And deep learning systems do beautifully at this, like surprisingly well. They generalize in ways that suggest they have relational abstractions. But along the lines I was talking about during the questions after my talk, this is their whole universe. They've been trained their whole lives to play this game. Human subjects walk in the room and you give them a short set of instructions and then they immediately do this task, even though it's a very bizarre task from the point of view of what they've done with the rest of their time on Earth. I just don't think we have any idea of how AI systems could have that kind of flexibility.
These are great. Let me just push a little bit more, and then maybe I want to pick up on this idea of emotion, of motivation, of curiosity, and thinking about intelligent agents and where that future lies 10, 20, 30 years down the road. And thinking about humans, I mean, the older I get, the more I'm convinced that emotion drives 85% or so of our behavior, right? I think rational reflection and thinking and planning, I don't know, we can argue about the percent, but I think a lot more is driven by emotion than by rational reflection and thought. What is a computer driven by? I mean, the computers, things we've talked about today are driven, they're minimizing error functions or something like that. And then who writes the error function? It's the programmer writes the error function, right? But I'm curious if we're really going to make agents or independent agents that are curious and explore what's their motivational structure, what's their equivalent to emotion. Or I think in a human-centered AI sort of meeting we had one Friday afternoon, I think John put it, what did you call it? You called it incentive structure or motivational structure. What's the motivational structure for an exploring agent, and what is it after, and could that agent possibly change its motivational structure on its own at some point?
I wish I had the answer to that. I mean, people think of surrogate answers, like maybe agents they're lazy and they want to minimize energy consumption while also, getting some external reward that somebody else has set up for them, right? Or maybe they want to understand the world and somehow compress the information and get a really short representation because that's somehow useful. But I don't think we really have the actual answer. I think these are good surrogate answers that are a lot driven by our intuitions and may not be the right thing really for automated agents.
So I think that in the applied AI world right now, the way that we craft a system to solve a particular problem is through organizing the data that the system are exposed to, through making architectural tweaks, but it's mostly by defining the problem, the task to be solved, and defining the objective that is going to be optimized. And then there's some calculus, right? And it's that kind of craft, and that's the main influence of the designer of the system, right? And in some sense, the motivational states that have driven all of this behavior were created, we think, by evolution, right? To drive making more of us. And personally, I'm not keen to build some robots that are whose main objective is to make more robots. I don't actually think that that's the productive thing that we want to do for human-centered AI. But I do think that what we want to do is we want to find useful intermediates about, well, how do I make it so that the objective for my navigation system on my phone is to try to get me there in an efficient way that's also safe, right? That's a much more abstract objective than just finding minimum path distances. And I do think that we want to move up the chain, but I think that we're actually going to spend a very long time in a state where we are actually the designers and the authors of what the objectives are, what the motivational states are of these systems.
So, there's been a lot of talk about bots interfering in political elections and such. So basically, bad actors released in the environment with cost functions, minimizing cost functions that are really socially deleterious. I mean, how much of a danger is that? Is it going to be we worry about our computer viruses? Is it going to be computer viruses on steroids? What about the motivational structures, bad ones that can get put in by humans for their own purposes?
So when it comes to AI agents and machine learning's implication to societal, structure and I think the danger is real, and it's not just this particular example. For example, there's a huge move in industry these days about fairness in machine learning, because while we are celebrating detecting cats on the internet, we suddenly get ourselves in issues of not fairly recognizing different kind of people and making possible legal decisions based on biased data. So in terms of AI social implication from disinformation to machine learning fairness to privacy issues to other ethical challenges, I think this is precisely the time and the moment in history that as AI scientists, as well as all of us should be thinking about and investing in our effort in. One thing I would like to emphasize is that I don't think this is a question that can solve only by AI scientists. I think AI scientist is part of this effort, but we've got to work with our social scientists and humanists, from ethicists to economists to legal scholars to policymakers. And I know I'm repeating myself, but here at Stanford and other places, we have the opportunity to involve these people. And even at Google, right, coming from Google, we know that there's a lot of discussions already taking place with ethicists and policymakers. And this is really critical time for that.
Yeah, I heard there's an ethics division at Google now. Is that true? No, you haven't heard of it?
There are a lot of divisions.
Okay, does anyone have burning questions that you'd like? Yep, I'm running over here. You've got that one, and I'll go a different place.
I run a small AI startup where we're building machines that could feel. And keeping the technology aspect aside, I got my answer actually answered from Fei-Fei on the policies and the regulations around AI ethics, both from the neuroscience perspective on the biology, as well as from the other perspective, we are trying to build robots that could feel the implication of that. What should be the regulations? And so my question is, how much we as scientists, faculties, should be involved in creating and formulating the regulations around some of these technologies. So Fei-Fei answered that, obviously, and I know her answer, but other people on the panel as well.
So we definitely need to be involved, but computer scientists are not qualified to think about ethics questions, in my humble opinion. I think perhaps future generations of students will just need to be trained more formally in some of these issues, but we really need to engage the social scientists on these questions. Otherwise, we're not going to be able to crack them.
Thank you very much. I really appreciate the comments about reaching across the aisle to other industries, especially ethicists and also folks who work on the policy side. I actually work in the policy side, so I'm very much wanting to collaborate. I work in a space where I work for local government here in the Bay Area, and I am responsible for evaluating smart city technologies that are coming up, that are programmed with algorithms that city government employees really just don't understand. And so we have to trust almost the public sector in saying, okay, we're going to assume that there are no algorithmic biases that are being programmed unintentionally in these systems, but we won't be able to test that really until we actually implement them and things come up from the woodwork from there, which can cause political backlash later on. And so, especially here in the Bay Area, we're trying as local governments to collaborate, but we're missing the technical folks at the table. So if there are opportunities to collaborate, there are policies right now that are being made around smart city initiatives. And there's a huge blank space right now, or an opportunity to discuss privacy issues and programs that are intentionally going to be governing the way people are going to be behaving and interacting in society. And so I agree, this is a critical time, and I do appreciate the comments and the work that's being done to create more of a collaborative effort. So any more information that you can pass along to governments here in the Bay Area and beyond would be greatly appreciated.
So I just want to quickly say, first of all, you're not alone. In the AI space in the past few years, I've heard so many sectors from governments, local or national, as well as industry, looking for this kind of guidelines as well as collaborations. And John and I, in thinking about Stanford's Human-Centered AI initiative, very, very much has this in our mind. We are going to initiate programs that are facing policymakers, that are looking at potential ideas of rating AI fairness and privacy and all this. And already, not only at Stanford, there are budding efforts like AI partnership that Google, DeepMind are all part of, and AI Now Institute and all that. So we're happy to share with the information, but this is something that at Stanford's HAI initiative we're very much going to focus on.
My question is, in listening to your beautiful presentations today, I was struck by the repeated use of terms like the brain and our brain, as though there is such a thing as uniformity among brains of different individuals. And I wonder, I understand that your studies are done by collecting data from different subjects and averaging and reaching conclusions. But I'm wondering about the extent to which individual variation is studied or taken into account in some of the studies, for example, the ones on object recognition and various other parameters that are being used to evaluate synapses and circuitry and things of that sort.
Yeah, so I have a particular perspective on that, and maybe the people disagree. Is that my view is that we're all beautiful, unique snowflakes. So we're all just crystallized water. So there is a tremendous amount of individual variation, and that is important, and that's actually tremendously valuable. But a big part of what I think both the scientific efforts and the engineering efforts are to understand, well, what are the organizational principles that are common, and what are the things that give rise to the variation, and how do we understand both the function of the variation and the risk that's associated with the variation. And so in the artificial intelligence community, we study the variation in our systems, and sometimes that's to try to control it. Sometimes it's to try to use it to our advantage. So a dirty little secret is that when you look at these winning competition numbers, the winner is always somebody who built what was called an ensemble, which means that they actually trained 3 to 10 individual models at 3 to 10 times the cost, and then they averaged or they voted or in some way combined their results so that they made a little committee, because that committee is often more accurate than any of these individual artificial systems. And we do that same thing with juries when we need to make decisions as groups of individuals. So we accept, I think we have to accept that there is individual variation, but both in AI systems, the way we build AI systems, and in organic intelligence, but our approach should be to try to understand how that comes to be.
Thanks for the inspiring talks. I learned so much, and I think from your talks I learned how with this field to move forward, we need knowledge from CS, we need data, we need engineering and psychology and artificial intelligence and neural network, and all of these concepts combined together. What I haven't heard is philosophy, that I also think is important, because over the summer I studied a course about introduction of philosophy of mind, and already heard a lot of this theories about dualism and behaviorism, functionism, and then representationism, which is I feel it's the Hatter theory kind of that a lot of work can categorize into under those philosophical ideas. So I wonder if you, just out of a personal interest, if you were inspired by any philosophical ideologies there, and if you think your work can approach, or is there any inspiring philosophical ideas that's intriguing and leading your work moving forward? Thanks.
So do we have any closet philosophers on the stage? And if we don't, I'm standing next to a professional one. And
So I was so Fei-Fei and I were both undergrads in physics together, but I was secretly trying to get an undergraduate in philosophy without telling anyone at the same time, and I it's a pattern. And I actually feel like some of those concepts in philosophy are as relevant as the concepts in neuroscience to how we think about problems and how we approach things. And one of the things about philosophy that I think is so valuable is the training in how to ask a question and how to identify what constitutes a valid answer to that question. And I think that that's extraordinarily useful and is actually part of the fundamental basis of how it is that we do science. In terms of the particular ideas, a lot of it was reacting to ideas in, for example, philosophy of mind, and being like, dualism, I don't believe that at all. I'm going to show that that's probably not how the world works, right? And reacting against these conjectures is actually, I think, an exciting and motivational experience.
So for a long time that people accept object recognition is a thing in computer vision, I had to start my talk with Plato, who talked about object recognition. But Alison Gopnik, whom I mentioned, is a philosopher as well as a cognitive neuroscientist, cognitive scientist, and she studied a lot about theory of the other mind and all that. So I'm not a closeted philosopher. I admire that you are able to do that in addition to your physics degree. But I think it's really important that we incorporate that. And indeed, John, my partner on HAI, is a philosopher.
Indeed he is. Let's swing over to this side of the room. I get scotomas and get too
Hi there.
focused.
So it was just a curious question I had when I launched my jobs like at the Compute Canada cluster yesterday. Do you think like evolution is the most efficient way that has happened that did like neural architectural search ever? And the next question is that do you think when we were born as a baby our brain weights are pre-trained?
The last question was the question I said I want the answer to, right? What does the birth state actually look like? We don't know, right? So a lot of it, though, is pre-trained, right? There's a lot of evidence that there is a lot of structure even at the time of birth. Now, how much in the decimal sense that I was trying to do, those are what we don't know. But that whole birth state, I mean, that is the inductive bias that when cognitive scientists say, oh, wait, the kids have this stuff in them, that is, in some sense, that's the anatomy magic. That is an inductive bias, and that's exactly what I think Matt was trying to say in his talk. And we don't yet know how to translate that into the terms of function that we like to talk about, but that anatomy provides the inductive bias, but we don't know that. So it's a great question, but I don't know that. Your first question was evolution. I would have said, clearly this is just one run of a process that probably exists many times, but I don't know, Planet Hunter talk, somebody could, I think that was whoever that was can tell us about how many times it's being run.
So the evolution question is an interesting one, but I actually think that we have some measurements. So genetic algorithms have been around for a long time, and we sometimes use them to search through architectures or design AI systems. And given the current speed and style of computation, it's not a good idea. So genetic algorithms are not, we try them routinely to see if the status has changed, but right now that's actually not how most of us are getting to the best architectures. In fact, to add absurdity to absurdity, we're using an artificial neural network to search for structures of artificial neural networks that are going to, segment other networks. So it's kind of turtles all the way down, artificial neural networks all the way down. So, but I do think that we have to be cognizant that that's just given the state of technology today, right? And it might be that genetic algorithms are kind of off to the side right now, and computers get 10 times faster or 10 times cheaper or I don't know what, and then all of a sudden it becomes something that happens in every lab.
It may also just be that, biological systems and artificial systems are just going to be fundamentally different answers to the same question. And so, maybe evolution is a really good way of doing biological stuff, but maybe it's never going to be a good way to do things in hardware, the kind of hardware that we build.
Maybe I'm just tired and my response threshold is lower because I really should not open my mouth. I know nothing about evolution. But it does strike me as a domain where looking to neuroscience might give us some interesting clues. In particular, what is the unit of selection? Evolutionary methods as we apply them in current AI work are often, highly unbiased. They, just let's figure out the whole weight matrix. Let's figure out the whole architecture. It strikes me as intriguing, and I'm sure there are whole libraries full of previous work on this. So, again, my response threshold is low. But it strikes me as intriguing that the brain has repeating structure everywhere you look. People like to say, oh, well, the cortex is just this repeating unit, and therefore that unit must be very important. But perhaps it's also the case that evolution works on repeating units, and that's why we see these repeating units. Another thing that you see all over the brain is gradients. Like some parameter is smoothly changing from the back of the brain to the front of the brain, or the back of the hippocampus to the front of the hippocampus. And maybe evolution is working on those parameters rather than just trying to figure out the whole weight matrix at the same time. So I don't know, maybe this is a place where neuroscience can guide our investigations to make evolutionary methods in AI more efficient.
Great. So here.
I'm glad that you're speaking about bias and evolution, because my question is related to why it is that AI is so specifically human-centric, and where you see exploration of the sensory perceptual awareness of other species playing a role in gathering data, and adapting that to a broader spectrum of what we speak of as AI.
Well, not sure exactly if I will be able to answer your question, but I think a lot of what we did in at least computer vision that is driven and inspired by human intelligence, visual intelligence, is because of the capability of human intelligence, like visual intelligence, the fact that we are able to recognize objects, to navigate space, to understand things, to socialize and perform actions. So that's where the original inspiration of human-centeredness come from. But a lot of the studies that, especially neuroscience, is not human-centered in the sense that the whole neuroscience inspiration come from mammalian studies, of mammalian visual pathways, and we learn a lot from fruit flies to C. elegans to rhesus monkeys and all that. So I think there is recognition of the broader animal spectrum and where we can take inspirations.
We have time for maybe a couple of more questions. The director's comments will be very short. I have control over that.
So it's great to see the sort of arc of the field, and for me as a psychiatrist and a neuroscientist, it really makes even more clear a much more fundamental problem that we're facing in seeing all this stuff come by and then figuring out how we make any sense of it. And that is, in fields like psychiatry, things like health, we face two fundamental limitations at least. One is we'll always have very few data for most of the kinds of data that we need. People differ, as was mentioned, tremendously, and actually it's in those differences that the key decisions are to be made. But even more problematic, we have not really and may never be able to operationalize what we're trying to understand. So if you have an image and you're trying to read out information from the image or from IT neurons, that seems quite doable. But how do we think about applying this kind of approach to sparse data on mood, on motivation, on behavior, when we don't even know how to really operationalize that?
I mean, I'll make a short attempt, which is that's in some sense I agree with the premise of your question, and in some ways I use that as a criteria for what are the fruitful applications of AI and machine learning that are immediately available to us. Is can we satisfactorily operationalize the task that we're trying to accomplish? And there may be subtasks in your field that we can operationalize about, the propensity for some patient to respond to a particular medication based on their genetic background, for example, or based on some behavioral observations that we're able to make. There may be sub-problems that we're able to operationalize and gain sufficient data around, and then that becomes an appealing target. But it's always going to be vastly outnumbered by things that we either don't know how to operationalize, or even if we do know how to operationalize it, we don't have a way of getting the observations, the data that would be required to meet the data standards given the current sample efficiency of algorithms. So we should always be selective and thoughtful about whether or not this is a plausible application, because if it's poorly operationalized, you'll have unintended consequences. If the data sets are too small, we know for certain that the systems will be biased and they will be ineffectual. So we have to choose carefully.
Okay, sorry.
So in terms of the amount of data, there are some things that one can do. There's deep learning, which is very data hungry. And then there are other machine learning methods which are much less data hungry and which have been used successfully on lots of medical data sets that have 100 patients, 50 patients, 200 patients, and so on. So it's also a matter of choosing carefully what kind of algorithm, but you do need to have a definition of what it is that you're trying to solve, for sure.
So can I just add to this perspective? You guys they're mostly speaking, if I got it right, as about how current learning algorithms, how much data they need to digest. But I would take a totally different tack on this question, which is, remember, part of the goal, if you want to, you're a psychiatrist, right? I'm trained as an MD, PhD, and we don't understand the brain. And Bill said this at the beginning. We want to fix brain disorders. taking some of these things as literal models of what's actually going on in the brain. And we're trying to fit the central tendency, it was already sort of pointed out, and then understand the variability on top of that. But if you actually have decent models of the central tendency of some of these things, and we're not yet up to full scale kind of mood tests and so forth, we're just talking about vision, about how many dimensions of vision we hold up high in our brain. We're closing in on that, then we can go to the variability, and then lower amounts of data will be needed, I think, to assess how one individual varies from another in terms of their high-level visual representations. And those variations almost certainly exist, we just don't yet know how to test them, but we're getting close to that. So a deeper understanding from these models should enable lower amounts of data to tell us where individuals sit on the spectrum of certain things. At least that's what I hope. I can imagine that in vision. I don't yet know how to think about that for very high complex things like mood and mood disorders and so forth. But I think all of us can imagine that with things like color vision as an example we already know about. But think about number of dimensions each of us code the world in objects. That it's not the same for each of us, but we could probably come up with tests that would be for each of us without that much data to assess us. And the models will allow that in the sense of a deeper understanding of the brain.
Okay, you have the last question. Go for it.
So, first of all, thank you so much for the wonderful talks. I guess in understanding cognition, there seem to be two sort of broader schools of thought, especially within the sort of theoretical neuroscience field. One of which is, I guess, Professor Boyden's approach of determining ground truth. In understanding the brain, we want to sort of find the fundamental building blocks, as we did with DNA, sort of in understanding the brain, we don't have that kind of fundamental building block yet. And the only way to discover that is to find this ground truth. Whereas the other school of thought is sort of a more theoretical approach, which sort of involves, finding theoretical models based on concepts taken from, psychology and from, various studies in neuroscience, and then building them into, say, deep learning models or into sort of computational models, which, and at a certain point we might hope that this would converge upon, sort of insights into understanding the brain and understanding cognition. Do you think, so I'm curious to hear what you guys think about this sort of dualism, whether it should exist in the first place, and also from the more theoretical point of view, sort of building off of the last question, if you fear that there's a possibility that we may never converge upon, understanding cognition in the sense that we may never fully comprehend consciously the mechanisms that are occurring in our mind.
Yes, it's a great question. I think we need both. I've had great conversation with Ed Boyden himself about this. We need both the bottom-up ground truth approach, we need the top-down theoretical approach, we need them to meet, we need them to talk to each other, we need the theory to guide us, to tell us what to measure in a situation where we have limited opportunities to measure everything. We need the experimentalists to say, hey, you guys aren't thinking about this, I think this is really important. We need it all. And I actually think that one of the greatest intellectual adventures of this century will be trying to understand how the mind emerges from the brain. It's too exciting of an opportunity not to pursue it, simply because we might think it's hard, right? To channel JFK a little bit, we do this not because it is easy, but because it is hard. And I think it's going to involve a nexus of all possible fields of human inquiry to really crack this problem, ranging from physics, math, CS, stats, experimental biology, and so forth. And actually, like Fei-Fei was saying, I think Stanford is one of the most exciting places to do this because of the institute you're building, SNI, and all this stuff. So I'm optimistic. I'm a glass is exactly how much water there is in it, and I think it's pretty high.
I think that's a fantastic note to end on. Thank you, Surya, very much. And